Hi everyone, I am Ahsanur Rahman from North South University, Bangladesh. I shall present our paper entitled A Fast Exact Algorithm to Enumerate Maximal Pseudo-cliques in Large Sparse Graphs. My student Ramiza was supposed to come and present it here, but she got very sick in the last minute, and as such, I am making this video presentation with the permission of the organizers. So, let's start. Graphs are often used to model real-world networks such as PPI networks, social network, and so on. A common problem in graph mining field is to compute dense subgraphs, which are defined in different ways in the literature, such as cliques, near-cliques, degree-based quasi-cliques, etc. Here we focus on pseudo-cliques, which are subgraphs with almost all possible edges. For example, in this graph, these four nodes create a pseudo-clique, but this is an informal definition. Formally, a theta pseudo-clique is a node set that induces a subgraph with density at least theta, where density is the ratio of number of edges in that subgraph and the number of possible edges. An L theta pseudo-clique is a theta pseudo-clique with at least L nodes. A maximal L theta pseudo-clique is an L theta pseudo-clique, none of whose supersets is an L theta pseudo-clique. For example, in this graph, 1, 2, 3, 4, 5 is a maximal 4, comma point 7 pseudo-clique, as it has at least 4 nodes and its density is at least zero point 0.7. But if we add any node with it, its density will fall below zero point 0.7. So it will no longer be a zero point 0.7 pseudo-clique. Now, why do we bother about pseudo-cliques? Because they have applications in finding protein complexes, co-regulated proteins, disease-related RNAs and genes, etc. Despite so many applications, there are little research on pseudocliques. Specifically, only two exact algorithms are described in the literature for listing pseudocliques, namely PCA and HOLTS. In absence of fast exact algorithms, aforementioned applications typically rely on heuristics, which indicate the necessity to develop faster exact algorithms for pseudo-clique mining, which is the goal of this work. We made several contributions here. We proved that pseudo-cliqueness is not a convertible anti-monotone property. Thus, existing pruning techniques for mining patterns with anti-monotone or convertible anti-monotone property are not applicable to pseudo-cliques. We derived some mathematical properties of pseudo-cliques and used those to develop some pruning techniques. We applied those pruning techniques on top of the PC algorithm to design a faster algorithm, which we call FPCE. We derived a tighter time complexity bound for FPC than that described for PC. We demonstrated superior performance of FPC over existing exact algorithms. We showed that all pruning techniques of FPC are useful for its speedup. We demonstrated an application of pseudocliques in protein complex prediction. On a high level, our algorithm extends the subgraph induced by the current theta pseudoclique key by recursively growing it in a smallest degree last ordering. Three cases may happen in a recursive call. Firstly, if it is not possible for any extension of the current subgraph to be an L theta pseudoclique, then we backtrack, skipping the costly child generation process, i.e., we prune the unnecessary parts of the search space, which is one of our major contributions here. Secondly, if the current pseudoclique P is a maximal one, then we print it. Otherwise, we generate and exploit the children of P in the recursion tree. Our fast pruning technique, namely order bound, is based on our observation that each pseudoclique has a certain maximum order that can be calculated by using this formula. Our second pruning technique, namely Turan filtering, is based on our observation that each pseudoclique contains certain R clique and that clique can be found in a certain R prime core of the input graph. So we first compute these R cliques and then extend them to maximal L theta pseudo-cliques. Our third pruning technique, namely S-bound, is based on two inequalities that we show here. If a pseudo-clique do not satisfy these inequalities, we keep trying to generate its children, thereby saving time. The pseudocode of our algorithm is shown here. Note that the most costly part of the algorithm is get children pseudo-clique procedure, which generates children of the current pseudo-clique. Also, bear in mind that order bound works during pre-processing. So when it holds, the entire search tree is found and no other pruning techniques need to be applied. We show a simulation of this algorithm on a toy graph shown on the left. The corresponding PCE recursion tree is shown on the right. Red branches are the ones that are pruned by FPCE. As you see, FPCE significantly reduces the search space of PC, even for this small graph. We created 16 synthetic graphs and collected 18 real graphs. All of them are sparse except these three real graphs. However, no existing exact algorithm finished execution on these three dense graphs. Our results on real graphs are based on these 15 graphs. The speed of FPC over PC is 3.1 and 6.5 on synthetic and real graphs respectively. It gains even greater speed up over odds. Here, boxed IDs indicate graphs satisfying the order bound, where we see huge speedups of at least 19. Since order bound prunes the entire search tree, this shows the effectiveness of order bound. To check the effectiveness of the remaining two pruning techniques, we create a variation of FPC, namely FPC minus EB, which lacks S-bound, i.e., it acts as FPC having to-run filtering only on graphs not satisfying the order bound. On such graphs, FPC minus EB gains a speed up of 1.6 and 2.2 over PC for synthetic and real graphs respectively, which is the effect of to-run filtering alone. If we add edge-bound on top of it, we gain even further speed up as shown here. So clearly, all pruning techniques of APC positively contribute to its efficiency. We show an application of pseudo-cliques for protein complex prediction. For this purpose, we compute pseudo-cliques in a PPI network using FPC and CL1, which is a heuristic pseudo-clique miner. We also compute DQCs in that network using fastQC, an exact DQC miner. We use a commonly used metric called accuracy to compare pseudo-cliques with known protein complexes, whose formula are defined here. Our results show that FPC outperforms both CL1 and fastQC in terms of SNS, PPV, and accuracy from almost all values of theta, while consuming similar execution time. Finally, we compared complexes predicted by FPC, CL1, and fastQC using number of matching complexes, i.e., known complexes that share at least three proteins with the predicted complex, and via GO-CC term enrichment of clusters found by merging overlapping predicted complexes. We see that no known complex matches with any DQCs, and all complexes matching with CL1 pseudocliques also match FPC pseudocliques, which show that they are less useful as compared to FPC pseudocliques. Also, many Go-CC terms are enriched in FPC clusters, but not in CL1 or fastQC clusters. However, the opposite is not true. It shows that FPC may be more useful to unearth protein complexes and or cellular components than heuristic pseudoclique miners or DQC miners. With this, I conclude. Thank you. If you have any questions, please contact me using this email address. Thank you so much.